All right, let's go over the homework that you were assigned. So starting with number 1, HCN. HCN is has multiple bonding because the carbon, remember, needs 4 bonds and there are only 2 things, and hydrogen will only make 1 bond. So when you count it out, and then when you write it out, it looks like this. And since the central atom is carbon and there are no lone pairs on the carbon, and this is a linear geometry with 180 degrees. Then for number 2, H2S is similar to H2O since sulfur and oxygen are both group 16 elements with 6 valence. So it's a bent structure. And since there are 4 domains, by domains we mean the pairs of electrons, so whether it's in a bonded form or in a lone pair version, they're still considered 1 domain each. So 4 domains, it's going to be about 109 degrees, more or less, maybe between 107 and 109. Number 3 is carbon dioxide, and we drew that before. Looks like this, and this is also linear with 180 degrees. All right, then we have sulfur dioxide. So let's look at sulfur dioxide, SO2. So there are 18 valence electrons, sulfur, and 2 oxygens that we need to account for. So we'll start with single bonds, and that's only 2 electrons. And remember, we just said we have 18, so that would leave that. The problem with this is that I think one of them doesn't end up satisfying. Let me see. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, and 18. So as you can see, this is a little different than the other ones in terms of the way it bonds. Here it's going to do should do multiple bonding. Okay, this is where the bonding gets a little tricky and strange, because oxygen is doing something that is not part of the normal. Here, as you can see, oxygen is not using any of its electrons to make this bond, but then the sulfur is having expanded octet. So this kind of structure is not something that you can necessarily know how to do. So I'm going to show you this, but when we're going to skip over it, we're just going to call it bent. Okay. And then NF3 is straightforward. You have nitrogen with 3 fluorines bonded to it. And then there's a lone pair on the nitrogen, and then the fluorines have their own lone pairs. And then since this is 4 domains, but in this case it's not tetrahedral because this is a lone pair here, the lone pair causes it to become trigonal pyramidal. All right, some of these other ones, like the NO3, these are polyatomic ions, CO3, SO3 with a 2-. These are all going to be something called resonance structure. So they're not going to do the normal things that you see with, HCN, where there's only one way to this. There's no other option. But when we're looking at something like NO3, and NO3 has a negative charge overall, when you're counting up the valence electrons, you have to add this 1 electron here. So nitrogen has 5, plus the 6 that each oxygen has, times 3, so that's 18, plus the 1 electron that comes from this charge. So now we have to account for 19 plus 5, 24 electrons. We just add the 24 electrons to make it so that it's stable and that everything has the number of electrons that it needs. So these kind of structures don't follow the regular octets in terms of some of them do expanded. Oxygen doesn't do expanded normally, but things like sulfur and phosphorus and even nitrogen sometimes. What happens though is this double bond here can actually move to be here. So when that happens, you draw the same structure, very similar, except that you have moved the double bond. And you can move that double bond also here to the other one and redraw it. And these are called resonance structures. Again, this only happens when we're dealing with this moving double bond. And usually it happens with polyatomic ions and a lot with the nitrogen. So like SO3 or NO3, O3, ozone also does resonance. So it's not part of the normal structure, but just keep in mind that it does exist. Now, let's look at this. This is the entire molecular geometry chart that I put a link to on the calendar. And what I want you to pay attention to is how the geometry changes depending on whether there's a lone pair or not. So if there are two bonded pairs, we saw that would be linear. The linears are 180, trigonal planar 120. When it bends, then it's going to start decreasing in angle. So there are trigonal, pyramidal, tetrahedral, or bent when there are 4 pairs of electrons around it. When there's 5 pairs of electrons, now if you think of 5 pairs of electrons, that's not an octet, is it? 5 pairs of electrons give me 10 electrons. So that would mean that it has expanded octets, something like PCl5. PCl5 will actually have an expanded octet where it's trigonal bipyramidal. And then we have things like seesaw, T structure, octahedral, square pyramidal, and square planar. All of those are expanded octets. All of those are exceptions to the regular octet rule. And the geometry is different depending on how many lone pairs there are. So there are a few examples that I'm going to show you now with that so you understand how it works. Let me pull up OneNote again. It kicked me out. Hold on 1 second. So when we're talking about PCl5, this would be, so this is an expanded octet. Okay, and it's an expanded octet, and when you look at the geometry, you can see 5, right? So that's trigonal bipyramidal. Then we have ones like SF6 where that becomes octahedral. So let's look at something like SF6. Again, that's very expanded octet. You're talking about 12 electrons surrounding the sulfur, but sulfur has the ability to do that. So sulfur, phosphorus, occasionally you'll see xenon do an expanded octet. I know we've talked about how noble gases don't really react, but xenon is the only one that has the ability to do that. Given that it has so many energy shells, it has space to hybridize orbitals and put valence electrons and put bonds as well. And then if there are lone pairs on that octahedral, so instead of a fluorine, if there was just a lone pair of electrons on the sulfur, then it would become a square pyramidal. If it was 2 lone pairs, then it would be square planar. With the PCl5, if it had a lone pair, it would be seesaw. And seesaw has 2 angles. So there's an angle of the 90, and then there's an angle of the more or less 120. If you just know the roundabout numbers, that's good enough. So in other words, you don't need to know that it's less than 90. If you just put 90 for that, it's acceptable. And for the trigonal pyramidal, if you just put 109.5 for these two, the bents and the trigonal pyramidal that has 4 along with tetrahedral, it's really good enough. It doesn't need to be more advanced than that. So Resonance, once again, is these double bonds. So when we look at something like ozone is O3, and so there are, it looks like this, and it does do a funny thing of moving this lone pair. So things that you really need to know in terms of resonance is if I give you one structure, so if I give you this, if I've already drawn it up and give you this, you should be able to tell me this version. If I ask you draw a resonance, that's really all you do. Okay, you draw the resonance, you can also put the lone pairs, but I don't need you to know more than that because it is a lot more advanced than you need. All right, so that's all it is, the vsepr, geometry, Lewis structures. So the next topic is naming compounds. So we're going to talk about naming and writing compounds. We'll start with ionic, and then covalent is really, really simple. With ionic, we'll start with just binary. Okay. Binary means that you have like a sodium with a chloride ion. You put them together, you get sodium chloride, right? You name it. The first name never changes. The second one, the anion, gets an IDE ending. And then how do you know what charges each one has? Well, you know that sodium had one valence, right? So let's draw the bonding. And you know that chlorine, before it becomes an anion, has 7 valence. So the sodium transfers its electron over. This is what makes sodium plus. This is what makes chloride minus. You put them together and it's NaCl. Well, what if they're not one-to-one? In other words, what if I have sodium, but there's oxygen around? So if sodium and oxygen want to bond, what do they have to do? Well, we have to start with valence electrons again. Sodium has 1. Oxygen has 6. Well, we know how much oxygen wants. It wants 2, right? So sodium has 1 to give. So what do? We bring in another sodium. Can we bring in as many sodiums and as many oxygens as we need in order to satisfy the octet? Yes, we can. So another sodium comes in, gives its valence electron to the oxygen. Now what has happened? You have 2 sodium ions that are positively charged. You have 1 oxygen that's -2. So what's going to happen is the sodiums are going to combine with the oxygen, but it's going to be 2 sodiums that combine with the oxygen. How about if we had calcium and calcium wanted to bond to bromine? So calcium, so now what you can start doing, instead of drawing out the valence electrons and drawing it out this way, find what kind of charge it would become. Well, calcium is a group 2. Group 2 is a metal, so that means it becomes +2. Bromine is going to become bromide, so -1. And we forgot to name this. This is sodium oxide. So calcium and bromine. If calcium is +2, bromine is -1, how many bromines do I need to neutralize the calcium? So basically you crisscross the charges to be subscripts. Calcium bromide. Okay. So let's say we have magnesium 2+, chlorine is -1. When we put them together, we're going to get MgCl2, and it's going to be magnesium chloride. Okay, so I have a binary naming, ionic compound naming and writing formulas worksheet. So you're going to go ahead and work on that for the rest of the class period. Turn it in on MyJag when you're done with it, and then we will review it tomorrow and go on to the next kind of naming. All right, have a wonderful day.